Hello and welcome to Lesson 7.3, Part 1. I'm thinking that I might split this lesson into maybe 2 or 3 parts, so I don't know yet. I'm going to see as I go. But this first part of the lesson, this is going to be the most important one because we're going to talk about understanding our exponent and radical rules. All of these rules we use to simplify radicals, and that is the context of this lesson. The overarching theme is simplifying radicals. Now, we've used these rules before. You've seen them before. But I am going to go through each and every one of them, talk about them. All right. Now, again, we've done simplifying radicals before. For example, let's say square root 48, right? Square root of 48, is that like 16 times 3? Or maybe you could just think of this as 4 times 12, right? And then you say, oh, well, square root of 4 is 2, and then this is 2 root 4 times 3. They say, oh, okay. That's 2 root 4 root 3, so that's 2 times root 3, which is 4 root 3. And done, right? And there I have simplified a radical. Now, we did that. We did that last fall, right? But the reason this is going to be a tad different is we're going to introduce variables, okay? And that will be the next video. But I want to talk about these rules a little bit, just because I think if you have a really strong understanding of these rules, then you'll be able to effectively simplify more efficiently, okay? So I'm just going to talk about them. Now, I will stipulate this. If you know all of these exponent rules, every single one of these things, if you know them by heart, you know them really well, skip. All right? Just skip it. If you truly know it, you know what you know, right? Skip this part. And then maybe focus on what I'm going to say towards the bottom down here about radical rules, because maybe that looks a little bit different. But I am going to talk about the exponent rules because there's a strong correlation or relationship between exponent and radical rules for a particular reason, and that's what we're going to tackle in this video. Okay, so let's officially start here with the product rule, right? So the product rule says, and notice one condition for all these exponent rules, I'm assuming A and B aren't 0. It's not necessary for every single rule, but I mean, I don't know. It's some of the rules need that condition, so we just put that there so we don't get in trouble, you know? Okay, so looking at this first one, I've got a to the power of m times a to the power of n equals a to the power of m plus n. We've seen this rule before. We've worked with it many times. This is the idea that x squared times x to the power of 5, I'm just going to say 3 because I don't want to draw that all out. X squared times x cubed is x to the power of 5, right? And we know this because, because x squared is x times x, and x cubed is x times x times x. And so how many times am I multiplying x? I'm multiplying it 5 times. So we call this the product rule because I'm multiplying 2 bases with exponents, right? 2 of the same base. And the result is I add those exponents. Similarly, the quotient rule, which is this one right beneath, is the idea that if I divide these 2 bases, then I will subtract their exponents. So suppose I have x to the power of 4 over x to the power of, 2. Yeah, that's fine. Then I will say that this is x times x times x times x is 4 x's. And down here is 2 x's. And you can kind of think about x divides x. So some of these cancel, right? Or divide out to 1. And so I'm left with x times x, which equals x squared. Which incidentally, right, is x to the power of 4 minus 2. So whenever you divide, you subtract the powers. When I move on to the product rule, I'm going to move over here to the left side so I have some more space and that doesn't get too crammed over there. The product rule basically says when I have an exponent on a base and I raise that term to another power, I then multiply the exponents. So to kind of see why that's true, let's say I have x squared cubed. And this rule would say that this is equal to x squared times 3, or I should say x to the power of 2 times 3, which of course equals x to the power of 6. Now, why is that true? Well, what we're doing is cubing the term x squared, which means we're taking x squared and we're multiplying that as a little triple, multiplying it by itself 3 times. Well, more like 2 times, but I don't want to get into the specifics of that. So x squared times x squared times x squared. And hey, we know by product rule that this is x to the 2 plus 2 plus 2, right? And you could think of this as x to the 2 times 3, which of course is 6. Yeah? So there you go. Yeah? I'm going to erase that part to keep this not too cluttered. But that's why that power rule works. Now moving on to the power of a product rule. This essentially says that it's almost like you can distribute this power onto those bases. This goes for both the power of a product and the power of a fraction or quotient. I can apply this power to both of these bases. So, example being, if I have x times y to the power of 3, then this equals x cubed, y cubed. And this is just a very basic property of multiplication. You say, why can I do that? Why is this true? Well, xy to the power of 3 is xy times xy times xy, which you could think of this as x times x times x and y times y times y, which of course is x cubed, y cubed, right? It's essentially just the commutative property of multiplication expanded out and then reordered. And that's all it is. I don't think I'm going to explain the fraction one because it follows the exact same logic, right? You could say that the x over y to the power of 4, that's going to equal x to the 4 over y to the 4. And really, it's for the exact same reason, okay? It's the commutative property of multiplication. That's why that's going to work out, okay? All right. Now, all of those you've seen before, and maybe you've skipped that, and that's honestly totally fine because being in Advanced Algebra 2, I would hope that you already know all that stuff. But if not, hey, there's the re-explanation. I hope it was helpful, okay? It's always good to revisit the basics, really. It helps so much. It really does. Okay, now here are the maybe 3 new rules you may or may not know, okay? I expect most of you to know all that stuff already. So you know what? I'm going to do that. I'm going to bracket this. I expect you know these already. I don't want to do a capital A. Already. Okay? I do. Because they're really more like Algebra 1 things. And maybe you know the 0 exponent one, but I don't know. Some Algebra 1 teachers, when they have to, make choices of, if I'm strict on time, should I cut this out or not? Sometimes they don't teach that. I don't know. So I'm going to focus on these 3 now because you may have not seen these before, and if you haven't, this is important. So I might even put a little yellow thing. You may not know these. Okay, so the zero exponent rule basically says when I have a base raised to the power of 0, that equals 1. And this is true for all numbers. Well, I'm not going to say except 0, but I will say that 0 to the power of 0 is an interesting case. And in fact, many mathematicians disagree on the meaning of 0 to the power of 0. However, that is its own video, and there are some wonderful videos out on YouTube exploring that if you are curious. But for the most part, for pretty much every other real number, you raise a real number to the power of 0, that result is going to be 1. Why? Why, right? Well, suppose I've got this. Let's say I've got x cubed divided by x cubed. Well, look, we know that x cubed over x cubed should equal 1, because whenever you divide some term by itself, that result is 1, right? I mean, you could even think of these as all 3 x's, right? All of those are going to cancel, get me 1, and that makes sense, right? But the other thing is, well, what did the quotient rule say, right? The quotient rule right here, I'm going to drag this. I don't want this document to get totally messy. But the quotient rule basically says when I divide these things, I subtract the exponents, right? So by the quotient rule, this is equal to x to the power of 3 minus 3. And 3 minus 3, of course, is x to the power of 0. So I'm going to say by quotient rule. Thus, so I might even say, therefore, x to the power of 0 equals 1. I mean, that's kind of a natural conclusion, isn't it? Right? If you're saying, okay, well, some term, I don't know what x is just some general case, right? X power of 3 over x power of 3, that equals 1. I know that for sure, but by the quotient rule, that's just 3 minus 3, that's x to the power of 0. And so if I'm just using x as a general number, that means any number to the power of 0 equals 1. And the reason 0 to the power of 0 is debated is because suppose that x is 0. Well, then isn't this 0 cubed over 0 cubed, which is 0 divided by 0? Now, there's a contention, right? There's something to be said about that. So if you're curious about that, go Google it. It's very interesting. It's really great because mathematicians don't agree on everything. Okay. If you ask Mr. Spake's opinion, Mr. Spake agrees with the part of the community that says it does equal 1. That's just my opinion. All right. Negative exponent. This might be very new. I don't know if you've seen negative exponents before. A negative exponent is when I have a to the power of a negative, whatever this number is in, I can write that as a fraction, as a rational expression, 1 over a to the power of n. So let's illustrate this maybe, okay? I might say, why does this work, right? So again, this is really just because of the quotient rule. So think about this. So let's say I have x to the power of 3 over x to the power of 4. Yeah? Well, I'm going to erase that error so I have some more room to write here. I'm going to work left and right here. I'm going to be kind of funny like that. First, I'm going to do the rightwards direction. X cubed is x times x times x. X to the power of 4 is x times x times x times x. And of course, 3 of those cancel, and it looks like I'm left with 1 over x, right? So, hooray, I've got 1 over x. But also, by the quotient rule, just like over here in the yellow, by the quotient rule, when I'm dividing these two expressions with exponents, this is x to the power of 3 minus 4. And what is 3 minus 4? It's negative 1. So therefore, right, I have shown, if you look at the left-handmost thing, right, x power of negative 1 equals 1 over x. So that's how we define negative exponents. So that's basically the rule. Whenever you see that negative exponent, put it in a fraction, shove it in the bottom. I can change this, by the way. If you wanted me to say, look, I will change it. I'm going to change it just for our notes. So, no, I won't change it for our notes. I like that. But just so you can see it in the context of this video, if I did x cubed over x to the 7th, well, that's x to the 3 minus 7, which is x to the negative 4, right? But there's 3 on top, 7 on bottom. 3 of those are going to cancel, and I'm going to be left with 1 over x to the 4th. So, hey, look, x to the negative 4th is equivalent to 1 over x to the power 4. Okay? Works for anything negative like that. One other thing to maybe mention right here while we're on the topic of this is this does work in the denominator as well. So if I have 1 over, let's say, x to the negative 3, think of that as flipping this up and writing this as x cubed. And you might say, well, why do we do that? Well, this is 1 over x cubed. And if you do your whole flippy fraction business, right, this is 1 divided by 1 over x cubed. That's just 1 times x cubed over 1, right, which is x cubed. So if you've got those negative exponents in the bottom, you can flip them, put them on top, okay? I know this isn't necessarily radicals, but part of this unit does include rational exponents, so this is where we kind of start that conversation, because you are going to encounter these things as we work with radicals. Okay, last one on this little exponential thing here is, I don't know, what do you want to do? Do you like blue? I hope you like blue. Is this rational exponent rule. And this is perhaps the most important new one to talk about. A to the power of m over n is equal to the nth root of a to the power of m. So in general, we can actually see that I'm jumping to radical rules for a second, but in general, the nth root of a we write as a to the power of 1 over n. And Mr. Spake is blanking as to why we use that notation. I know I've learned this before, but my brain is having a poof moment. So maybe this is something I can talk about in class, yeah? I'm not going to waste your time in the video if I don't remember on the spot. But perhaps give me a reminder to explain why this rule is how it is. But the basic idea is, I'll give you an example. We'll move in blue over here. Let's say I have x to the power of 2/3. I am going to write this as the cube root of x squared. Okay, that is basically what that rule says. X to the power of 2/3, that fractional part, the denominator, indicates the root, and the numerator indicates the exponent. I might write that down in your notes, right? the numerator is the exponent, and the denominator is the index of root. And remember, we talked about index in the last video, right? The nth root of something, blah, 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 blah. The index is the little number there, okay? So burn that into your brain. You must know that by heart. You must know it fluidly and be able to go back and forth between these things. I am going to illustrate a quick example with a number because I would like to do so. Suppose I was looking at, let's say, what does Mr. Spake like? I'm going to say 216 to the power of 2/3. I'm just going to use 2/3 again because I like it. 216 to the power of 2/3. Now, look, you could be sly and use a calculator on this, but let's think about this creatively, right? If I use this rule that I've listed up here, this is the cube root of 216 squared. Well, shoot, right? Shoot. Darn. What? How do I can I square 216 and then take the cube root of that? Blah, right? Well, hey, looky, we actually have an extension of this rule in this table here, right here. Notice, I'm going to put my laser pointer here. The nth root of a to the m, which is kind of what we've got here and here, right, can be rewritten as the nth root of a to the power of m. You can put that exponent inside the root on the radicand, or you can move that exponent outside of the radical and just have it apply there. And both of these expressions, this guy and this guy, are equivalent to this a over a to the power of m over n business. So this is also 216 to the 2/3 equals cube root of 216 squared. So now, if you knew what 216 squared was and you knew that you could take the cube root of that, then that would be fine. But it's much easier to analyze this as the cube root of 216, which is 6. Hopefully, hey, you should know that, by the way. Cube root of 216 is 6. And then 6 squared equals 36. Okay? So this rule can be very useful when simplifying some of these numbers, okay? Because I don't want to write it as 216 to the power of 2/3. I want to write it as 36, if I can, all right? To explain why this is allowed, well, I will put an asterisk next to this. You don't need to know this, but I want to explain it for understanding. If you think that this is too much, skip ahead a little bit, okay? I don't mind. It's fine. But if you are curious and you care and you really want a solid understanding of this, keep listening. So why can I say that the nth root of a to the m is equal to the nth root of a to the m, right? Why am I allowed to do that? Well, I am defining a to the power of m over n as the nth root of a to the m, right? So if I look at this as, we're going to use what's it called? The power rule. Sorry, right here. I'm going to use the power rule of exponents here. If I look at a to the power of m over n, you can rewrite that as a to the power of 1 over n to the power of m. Why, Mr. Spake? Why can you do that? Well, look. right? A to the m over n equals a to the 1 over n times m. Now, that, because they're being multiplied, if you invoke power rule, so I'm going to say power rule, I can rewrite that as a to the 1 over n to the m. And because of that, well, a to the 1 over n, that's the nth root of a. And then that's being raised to the power of m. Okay? So they do work, they do flow, and it's all because of exponent rules, right? All these radical rules come from the exponent rules. That's just why they work. Because we define all these radicals as rational exponents. So these are really just exponent rules in disguise. Okay. So yeah, okay. I've covered this one. A normal root, we just used that. Normal root, this is just how we define the nth root as a rational exponent. I think I skipped the definition of a root, so let me revisit this. You should really know this definition. Hint, hint, there's going to be a true or false section on the test. I don't know who told you that, but there is. There's going to be a true or false section. So, and this is going to be one of the questions right here. Actually, this one, and this one, and this one, and this one, and this one. So you might want to know those. Okay, but you didn't hear that from me. All right. So definition of a root: if a to the power of n equals b, then a is the nth root, is an nth root of b. Okay. This is essentially because, look, if I have, I'm not going to keep this, but if I have a to the n equals b, if I take the nth root of both sides, then that means a equals the nth root of b. Yeah? In fact, I'll rewrite that just so I have that here. Definition of root. If I say a to the n equals b, then I take the nth root on that on both sides. Therefore, a equals the nth root of b. So do you see how a is an nth root of b? It literally says it right here. A equals nth root of b. Yeah? Okay. Product rule and quotient rule. These fellas, well, those are the exact same product and quotient rules here. Okay? They really aren't any different. I mean, I guess they are different because you're not subtracting anything. Maybe I should be careful because it's a different kind of product rule. This product rule says that when you multiply two radicals, you can stuff them under the same radical. And you know that because we've done that before. That's not new, right? But I think that comes from this rule, the power of a product. Yeah, power of a product rule. So it's not that it doesn't come from the product rule, it comes from the power of a product rule. Essentially, if you've got the nth root of a times the nth root of b, well, we define the nth root as a to the 1 over n times b to the 1 over n. And if you use that power of a product rule up there, you know that you can smush that together as ab to the 1 over n, which is equal to the nth root of ab. That's why that works. Okay? You can make a very similar argument for the quotient rule, but I'm not going to do that. I think you can just trust me on that, right? Unless you're curious, you really want to try it out for yourself. See if you can kind of prove that. Okay. Last two things, and then I'm done with this video. I don't know how long this is. I hope it's not over 20 minutes. If it's over 20 minutes, I'm just sorry. That's all I got. I'm just sorry if it's over 20 minutes. But these last two things here, there is no additive property for square roots. So don't be making that mistake. I put this here, and I put it in red, and I put an asterisk here because a lot of people make this mistake. Even people that know math really, really well sometimes make this mistake. Maybe they just forget. But if I have the square root of 2 plus the square root of 3, that is not equal to the square root of 5, okay? You can't add square roots that way, okay? You can multiply them. It's true to multiply. I can say square root of 2 times square root of 3 is square root of 6. That is true. But the addition property, that does not work. And it doesn't work for the same reason it doesn't work for exponents, okay? When you have x squared plus x cubed, those aren't like terms. You can't combine those, right? So there is no addition property. Just be careful of that, okay? Be on the lookout for that. You don't want to make that mistake. Okay. And finally, the last little thing here. This is probably what I'll record in part 3, or maybe I won't make a part 3 and I'll just teach it in class. I don't know. But we're going to talk about conjugate radicals. And so you can see these radicals here, x root a plus y root b. The conjugate of that is x root a minus y root b. And I know that that looks a little complicated. It's like, oh my goodness, there's 4 letters and all this business. But remember, we talked about conjugates in the context of imaginary numbers, a plus bi. What's the conjugate of a plus bi? It's a minus bi. That's it. You pretty much just flip the middle sign, and that's it. By the way, be careful. It's not negative a minus bi. You don't flip all the signs. You're only flipping that sign between them. Because a conjugate just looks at the difference between the two terms. So if you start with subtraction, you're subtracting between them. Do a double subtraction, that becomes addition. If you're doing addition, just change the subtraction, okay? And that's kind of the basic idea. It looks a little bit more complicated with this x root a business. But really all that is, here's a quick example, is like if I said 2 plus square root 3, the conjugate of that is 2 minus square root 3, okay? If I said 2 root 3 plus root 5, the conjugate of that is 2 root 3 minus root 5. Do you see? That's all you're doing, right? That's it. That is all you're doing is you're just flipping that sign. And this goes vice versa. If I gave you the minus, you just put the plus instead. Okay? And that's conjugates. We're going to use conjugates to help simplify radicals that are in the denominator. Same reason we simplified them with imaginary numbers, but like if I have 1 over 1 plus root 2, we're going to simplify that by multiplying by the conjugate, just like we do with imaginary numbers. But that's its own video, so we're not going to talk about that too in depth here. Okay, there it is. That's all the rules explained in depth to the largest extent that I can, just off the top of my head, because I don't have any script in front of me. This is all just knowledge that's just in my brain, and I am just dumping it here. So I hope this helped. I hope you liked it. And yeah, and remind me why we use a fraction for this. I need to look at that again. But yeah. Okay. Have a good night or day or morning or whenever you're watching this, and I'll see you next time.